Greetings, Mr. Sutton here with the AB Calculus 311 homework solutions on derivatives of logarithmic functions. On this problem, we're given the function x ln of x squared, and we want to find its derivative. So to make our lives a little bit easier on this, we could use the log pop-out rule to pop this 2 exponent out as a coefficient. So I can put the 2 out here with the x and write this as 2x ln of just x. That's going to make it a little bit easier, but I'm still going to have to use a product rule in order to differentiate this. So I've got u prime v plus uv prime. Let me set up my box and ribbon to organize things. I have factors of 2x and ln of x. Derivatives of those are going to be 2, and ln's an easy one. That's just 1 over x. Using the ribbon now to put it back together, I've got 2 ln of x, and then plus 2x times 1 over x. But this is really 2x over x, which just reduces to 2. And is that one of the answer choices? Doesn't look like it. However, using the rules of logs, we can actually pop this 2 back in as an exponent on the x. So if I wanted to, I could write this as ln of x squared plus 2. And that is one of the answer choices, choice B. On this problem, I've got the function ln of radical x, and I want to find the second derivative of that. Well, let's start by finding the first derivative. I'm going to start, before I even do that, by using some log rules to make this a little bit easier to work with. Right now I have an x to the 1/2 power inside. I can pop out that 1/2 power as a coefficient in front of the log just using log rules. So I can rewrite this as 1/2 ln of x. And now just taking the first derivative of this, I'm just going to have 1/2 times the derivative of ln, which is 1 over x. Let me go ahead now and take the second derivative of this thing. Let me rewrite this first, though. This is really 1/2 times x to the negative 1. And now to take the second derivative, I'm just going to use the power rule. So multiply negative 1 by 1/2. That's negative 1/2 x to the negative 2. To match the answer choice, I have to put this in fraction form again. So this x can move downstairs to be with the 2. We'll end up then with negative 1 over 2x squared, which is going to give us choice B. For this calculator-based problem, they're giving us two functions. F is the ln of x squared plus 1, and g is x to the 5th plus x cubed, so different types of functions. The line tangent to the graph of f at x equals 2 is parallel to the line tangent to the graph of g at x equals a. And a is some positive constant. So based on that, they want the value of a. Okay, so the idea here, basically, if we have parallel tangent lines, that means if I plug 2 into the derivative of f and a into the derivative of g, then that should give me the same value. So to start this off, I'm going to actually find the derivative of f and g, and then I'll plug those things in and set them equal. So for f prime, we need the chain rule. We have the derivative of ln of something. So that's going to be 1 over the something, so 1 over x squared plus 1, times the derivative of the something, so times the derivative of x squared plus 1. So we've got 1 over x squared plus 1 times 2x. That's our tail there. And then for g prime, we're going to have 5x to the 4th, just using the power rule, plus 3x squared. And now they're saying if I plug 2 into f prime and a into g prime, those two things should be equal. So we've got basically f prime of 2 equals g prime of a. Now f prime of 2 we can do pretty quickly here. That's just going to be 4 over 5. And g prime of a is also pretty easy. We're just replacing the x with an a. So we have 5a to the 4th plus 3a squared. And at this point all we're doing is just solving for a. Okay, well, this is going to be a little bit thorny to do if I try to do it with algebra, and it is a calculator problem. Looking at the answer choices, they want us to use the calculator here, so we're going to go to Desmos for this one. So on Desmos, I'm going to graph each half of this equation as its own sort of function. So I'm going to have y equals 4/5. And now let me also do y equals, and I can't use a, I have to use x, just the way Desmos works. So we'll do 5x to the 4th power plus 3x squared. And I just need to see where these two graphs intersect. Now they wanted a positive value of a, so I don't have to worry about this intersection over on the left. So it's just the one on the right that I want to see here. And I can zoom in if I want. I can set the x scale. Let's just make this like negative 0.3 to positive 1.1, just based on where my answer choices are. And we see here we have this intersection at about 0.447. So here's the screenshot of what I just did there. So we can say a equals 0.447, rounding that off, and that's going to be answer choice C. On this problem, I'm trying to find the derivative of sine of x to the x. So since I have a variable in both the base and the exponent, and there's no way to simplify myself out of this situation, I'm going to have to use logarithmic differentiation. So I'll start by taking the ln of both sides of this equation. On the left side, I've got ln of y. On the right side, using my pop-out rule, I have an x that pops out, and then I have an ln of sine of x. Now let me just take my derivative implicitly. On the left side, this is going to be 1 over y times dy over dx. On the right side, I'm going to have to use a product rule. So I have an x and an ln of sine of x. Derivative of x is 1. Derivative of sine of x, that's going to be 1 over sine of x times the derivative of sine, which is cosine. So I'll just put the cosine up here. And just looking at the answer choices, it looks like maybe it would be helpful if I just simplify this to cotan of x. All right, so now multiplying this out with the ribbon, I've got all this stuff equaling ln sine of x plus x cotan of x. Getting there. Now I have to isolate dy over dx, so I'll multiply both sides by y. And this is good as far as it goes, but you'll notice that all the answer choices have just x's in them. So I'm going to have to replace this y with the original function that it equaled, sine of x to the x, put that out in front there. And now this is hopefully going to match one of my answer choices. So I have, let's see, a sine of x to the x. So that's going to eliminate answers A and C. I also need an ln of sine of x inside there and an x cotan of x. So that looks like choice E. For this one, we have this function x squared plus 2x, and we want to take the derivative of f of ln of x. So probably the easiest way to do this is just to substitute ln of x for x in the f function. So just write ln of x squared plus 2 times ln of x. And now just take the derivative of this thing from left to right. So derivative of this first term, we've got the power rule. This is going to be 2 times something to the first power, so 2 times ln of x. But then we have to multiply by the tail, the derivative of ln of x, which is 1 over x. And over here, derivative of 2 ln of x is going to be 2 over x. Does that match any of the answer choices? Well, this first term, I guess you could think of as being 2 ln of x over x. And that gives us a common denominator with this other one. So we could say 2 ln of x plus 2 over x, combine them, and then that's going to give us answer choice A. On this problem, we want the derivative of ln of x. So this is going to require the chain rule. First, we have the derivative of ln of something. Well, that's just going to be 1 over the something, so 1 over ln of x. But now we have to take the derivative of the something. The derivative of ln of x itself is 1 over x. So 1 over x ln of x, then, choice E, is going to be our answer. On this problem, they're telling us that f of x is ln of x, and they want us to find the limit of f of x minus f of 3 over x minus 3. So this is one of the limit definitions of the derivative. This is the Leibniz limit definition of a derivative. Basically, they're asking you to take f prime here and plug 3 into f prime. So let's first find f prime. That's the derivative of ln of x, which is just 1 over x. And now they want us to do f prime of 3, which is just going to be 1 over 3. So that's answer choice A. On this one, they want the slope of the line tangent to the graph of ln of xy equals x at the point where x is 1. So basically, we have to take the derivative of this equation and figure out the slope, the value of the derivative at x equals 1. Since y is kind of tricky to isolate on this one. I'm going to use implicit differentiation. So derivative of ln of xy, ln of something, that's going to be 1 over the something, so 1 over xy. But now I'm going to have to multiply by the tail, the derivative of xy itself. And for that, I'm going to need a product rule. So let me put my box and ribbon to work here. We've got a factor of x and y, and the derivatives of those are 1 and dy over dx. Using the ribbon to put that back together, we've got 1y, so y up here. I could multiply it out here in a parentheses, but why not just stick it in the fraction, right? Because there's just a 1 up here otherwise. And then going the other way, we have x times dy over dx that we're adding in here. So that is the whole derivative of ln of xy. And that's going to equal the derivative of x, which is just 1. All right, well, to isolate dy over dx, let me first get rid of this fraction by multiplying both sides by xy. So we have the xy times 1, which is just equals xy there. Next, let me subtract y from both sides. And I can also divide both sides by x. Okay, so at this point, I need to plug in the x value 1. Only we notice that there's also a y in here. So you might have noticed that if you plug 1 in for x, you're going to have 1y minus y, which is going to be 0 no matter what y is. But if you wanted to find the y value before plugging everything in, you could. You can plug 1 in for x in the original equation up here, and then just solve for y. So if ln of y equals 1, well, if you raise e to both sides, you're going to get y equals e to the 1, or just e. So now we can plug in the x value 1 and the y value e to this derivative here. So up top we've got the x value 1 times the y value e minus the y value e all over the x value 1. And just like we kind of predicted here, we get 0 in the numerator. So that's going to zero out the whole fraction, giving us answer choice A. On this problem, I've got the equation ln of 2x plus y equals x plus 1, and I want the derivative. I'm just going to use implicit differentiation because otherwise it's kind of a pain to get that y by itself. And although I could isolate y, I noticed that I have y's in my answer choices. So this is probably going to be an imp-diff kind of situation that's going to lead us to one of the answer choices. All right, so on the left side, we have derivative of ln of 2x plus y. That's going to be 1 over 2x plus y, so 1 over something, times the derivative of whatever's inside here. And I'm just going to put that directly in the numerator. So that's going to be 2 plus the derivative of y is dy over dx. And all of that now is going to equal the derivative of x plus 1, which is just 1. To isolate dy over dx, let me start by multiplying both sides by 2x plus y. Since there's just a 1 over here, we just get 2x plus y on the right side. And now just one other quick step here. I'm just going to subtract 2 from both sides. So dy over dx is going to be 2x plus y minus 2, which matches exactly answer choice B. For this problem, we've got this crazy-looking piecewise function with a log function in it, and we want to know which of these statements are true. So we're talking about the left and the right side limit at the border value matching up, the derivative limits matching up at the border value, and then differentiability. All right, well, let's start by finding the left and the right side limits. That'll at least shed some light on statement number 1. Left side limit, as x approaches 1 from the left, that's going to be basically plugging 1 into this first rule up here. So 3 times 1 minus 2, that's going to give us just 1 for that limit. And now the right side limit at 1, now we're going to plug 1 into this bottom rule here. So we've got 3 times 1 minus 2, which is 1, but we're taking the log of 1, the ln of 1, which means we're going to actually end up with 0 for that one. So we see here that the left and the right limits do not match up. So that eliminates answer choice 1, or at least option 1. Now, since the limits don't match up, that actually has more implications for what we're doing here. That means the limit in general does not exist at 1, which means our function is not continuous. Since our function is not continuous at 1, that means it is also automatically not differentiable at 1. So that means we can also eliminate option 3. Well, that was some good mileage for that little experiment there, but we got to keep going. We need to now look and see if at least the limits of the derivatives match up, because we haven't got enough information to eliminate option 2 yet. So the left side limit of f prime. That's going to be, let's take the derivative of this first rule, which is 3. Now, if you plug 1 into the constant 3, you just get 3. So that's our left side limit of our derivative of f prime. Our left side limit of f prime, not the derivative of f prime, just f prime itself. All right, now we need the right side limit at f prime. So now we need the derivative of this bottom rule. That's going to be 1 over 3x minus 2 times the derivative of 3x minus 2, so 3 in the numerator here. If I plug 1 into this expression, I've got 3 over 1, which is just 3. That does match the left side f prime limit. Since these match up, that means actually option 2 is correct. So choice C then. On this problem, I want the derivative of ln of cosine of pi over x. So this is just a big mess. There's going to be a big chain rule involved here, and then we're probably going to simplify afterwards. Let me start by rewriting pi over x as pi times x to the negative 1. So when I get to the very end of my chain, I can at least use a power rule there. So now let's start on the outside and work our way in. We start with the derivative of ln of something. So that's going to be 1 over the something, 1 over cosine of pi x to the negative 1, times the derivative of the next function in. So that's cosine of something. Derivative of cosine of something is negative sine of something. So negative sine of pi x to the negative 1. And then finally, we need the derivative of pi x to the negative 1. Using our power rule, that's going to be negative pi x to the negative 2. Now we have to actually match one of these answer choices. So I see that I have a negative and a negative. That's going to give me a positive. And let's see here. I also have a pi, and I can write this as pi over x squared. So that's going to be out in front. And then let's see here. I also have sine of pi x to the negative 1 and cosine pi x to the negative 1. Sine over cosine, we know that we can write that as tangent. So this is going to be tangent of pi x to the negative 1. But I can put this back in fraction form and write this as tangent of pi over x. So that's going to, at long last, match answer choice E. At first glance, this problem looks like we've got some chain rule going on and some logarithmic differentiation. But if you look closely, this is actually a pretty easy problem. The key here is recognizing that we have e to the ln of something. E and ln, when you have this setup here, those cancel each other out. So you actually just end up with whatever was inside the ln, which is x squared, coming out of the exponent. So we really just have x times x squared, which is really just going to be x cubed. Well, that's an easy derivative. Just using our power rule, that's 3x squared. And all the answer choices were simplified anyway, so if you did go to all the trouble of some advanced techniques, you would have had a lot of work to get it down to 3x squared. But we can pick that now. Choice C.